This video is on section 6.1 notes, the standard normal distribution. So before we had talked about discrete random variables, and today we're specifically going to talk about continuous random variables. So a continuous random variable has a uniform distribution if each of its values has an equal chance of occurring. The graph of a uniform distribution results in a rectangular histogram. And you can see kind of a picture of this rectangular histogram down here. So this is a probability distribution in graph form. This allows us to see two very important characteristics. The first is that the area under the curve of a probability distribution is equal to 1. So down here, we're going to get to this specific problem in a minute, but we know that the area, when we talk about the probability of multiple different things happening, all of those probabilities summed together must be 1. It must be 100% of all of the data that we would have. And there's a correspondence between area and probability. Which allows us to find some probabilities by simply computing a specific area under the curve, which is what we're going to do in a second. So when we were looking at section 5.2, section 5.1, we were talking about binomial distributions, and that was because we had discrete probability distributions. We had values for our random variable that had to be specific. They couldn't be decimals in between something. They had to be very specific numbers, maybe the number of people or something similar to that. And here we're going to talk about continuous probability distributions, which is where we get normal probability distributions from, and that's because we're going to have measurements like time, where you could have 1 minute, 2 minutes, 3 minutes. You could have those kind of discrete measurements, but you could also be a little bit more precise. You could have 1.2 minutes. You could have 1.25 minutes. You could have 1.2578643 minutes. You could always get more precise with your measurements depending on how what tool you have to measure time. And so whenever you have something like that happening, we're going to use this normal probability distribution. So the example here says, during certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes. Find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. So we know that this overall area is 1. The probability of all of these wait times together has to be 1, has to be 100% of all the information that we have. And we know also from previous math courses that area is length times width. So if we want to know, this is P of X, this is the probability of X, or probability of whatever specific waiting time we need. If we want to know what specific probability this is that you're going to wait for 1 minute, or 2 minutes, or 3 minutes, or 4 minutes, or 5 minutes, if we want to know that probability, we simply need to say that the area is this length, and it doesn't really matter which one you call length and which one you call width, but is that length of 5 minutes times some width of this value here that's the probability. So 1 would be 5 times 1/5, or if we want to do that as a decimal, we would say 0.2. So 0.2 is the probability. Now that's not the answer to the problem, that's the probability for each of these values. So right here, this is a 0.2 probability that you wait 0 minutes, that you wait 1 minute, that you wait 2 minutes, that you wait 3 minutes. It's a 0.2 probability. So if we want to find the probability that x is greater than 2, that you wait at least 2 minutes, then that means that we're going to cut this right here at the 2, and we're going to find this area right here. What's the probability that you're waiting at least 2 minutes? It's going to be this portion right here. So we're going to have 0.2 multiplied by a width of 1, 2, 3, multiplied by a width of 3. So from 2 minutes to 5 minutes. And that's going to be a probability of 0.6. So you have a 60% chance that if you're a randomly selected passenger, you're going to wait for at least 2 minutes. So that's a way that we could use the area of something, area formulas and what we know about area, to help us compute probabilities if we have, excuse me, a uniform distribution, because this is just a rectangle, so it's fairly easy to work with. All right, next we have the standard normal distribution, which is for the random variable z. And that's because z-scores use the variable z, and it's a normal distribution with the following characteristics. So the distribution is bell-shaped. The mean has a specific value where mu equals 0. Remember, the population parameter of the mean is represented with the Greek letter mu, so mu is 0. The standard deviation has a specific value of sigma equals 1. And the total total area under the curve is equal to 1 again. So here this area is 1. So this would be a standard normal distribution, specifically using a bell curve. So we've looked at the bell curve before, we've looked at the empirical rule. This is going to be somewhat similar to that, but we haven't looked at one specifically before where the mean has to be 0 and the standard deviation has to be 1. So that's what makes this a little bit more specific, and that's what makes this a standard normal distribution. All right, so now we're going to look at an example with this. It says, a bone mineral density test can be helpful in identifying the presence or susceptibility to osteoporosis, a disease that causes bones to become more fragile and more likely to break. The result of a bone density test is commonly measured as a z-score, and the test results meet the requirements of a standard normal distribution. And those requirements are what we just said. Bell-shaped, the mean is 0, the standard deviation is 1. We know the area under the curve is going to be 1. That's how probabilities work. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score less than 1.27. So that means find the probability that this person has a z-score less than 1.27. So we've worked with the empirical rule, and we knew that if they had a standard deviation that was 1, 2, or 3, or negative 1, 2, or 3 away from the mean, we could kind of calculate what percentage. We knew the different percentages, but we never worked with something like this. We never worked with 1.27. We only worked with those integer values, those whole numbers. And so when we work this way, we have this table that you'll need to print. We're going to use this for the rest of the semester, so you want to have this handy to be able to use during tests and then during your MyMathLab assignments, and then when you take notes. This table that has the standard normal distribution values on it. So you can see on one side it has z-scores that are negative. On the other side, it has z-scores that are positive. So the first thing that I want to do is kind of go over how to read this table and kind of explain how it works. So when we find this probability that you have a bone density test score less than 1.27. This is kind of how the table is set up. It's set up to find the probability from the left side like this of values that are less than. All right, so we're gonna write this. I wrote this on my table. You can write this on yours. If you think you'll remember it, that's fine. So I wrote this version of the table. Provides probabilities for less than statements. So you're finding the probability that Z is less than some number. That's what this table does. And it's not that I had the choice of two tables and I picked one. It's that this is kind of how the tables are set up. Okay? So when we look at these values here, the inside right here, these are all the probabilities that are represented by this shaded area. Okay, so these are the probabilities given in the table. And you can see on this side we've got our negative z-scores. They're on the left half of the table. These are values that are smaller than the mean. And so if you look at these probabilities, they're all probabilities that are 50%, 0.5 or less. And then over here we have our probabilities that are more than half. These are positive z-scores. And so all of these we start with half, 50% probability and more. And so you can see that they kind of go up. All right, so the probabilities that are given, these are the areas of the shaded region or the area under the curve. Now, along the side down here, this column and then this row over here, both of those are the z-score. So the column down the left side gives you the ones place of the z-score and the tenths place of the z-score, the first digit. The row across gives you the hundredths place of the z-score. So you have your first decimal place and then your second decimal place here. So if I wanted a z-score of negative 1.43, I would look right here, negative 1.43, and then that would be my probability right there. So that's the way that the table works, okay? This is the ones place, the tenths place, and then the hundredths place, and you kind of have to find them together. All right, so let's go ahead and try this problem. It says, what's the probability that the z-score is less than 1.27? That's a positive z-score, so I'm looking on this side. Along the column, I'm going to look for 1.2. And then over here, I'm going to look for the 0.07 for the hundredths place. So it's 0.8980 is the probability, 0.8980. All right, and if you look, you should be able to say, well, that looks like, 89% or 90% of this is shaded. Yeah, that kind of fits because we know that area and probability have a direct relationship. All right, the next problem, example problem says a bone density test result above -1 is considered to be in the normal range of bone density test readings. Find the probability that a randomly selected person is in the normal range. So above -1, here's -1. All right, now the table does not give us values above -1. It gives us values below -1. So first, I'm going to find the probability that z is less than -1. And so I'm going to look on the negative side. -1 exactly, -1.00. That's 0.1587. And that is this portion right here, 0.1587. So if I want to know the probability that you're in the normal range, that the reading is greater than -1, then I need to take the entire area of 1 and subtract off the 0.1587. .8413. Okay, the next one says, a bone density test reading between -1 and -2.50 indicates that the subject has osteopenia. I have no idea if that's how you pronounce it, so somebody correct me if I'm wrong, which is some bone loss. Find the probability that a randomly selected person has osteopenia. So -1 to -2.5 is right in there. Okay, so we already know the probability that z is less than -1. That was 0.1587. We can find the probability that z is less than -2.50. That would be this part right here. So let's look at our table. So -2.50, 0.0062. And so if we want just the shaded area between the two, then I'm going to take the shaded area from the first one, which is this whole thing, and I'm going to subtract off the shaded area from the second one, which is just this part right here. So the probability that z is in between -2.5, I didn't leave enough space, so sorry about that, between -2.5 and -1 is the probability that z is less than -1 minus the probability that z is less than -2.5. So you always do the rightmost probability minus the leftmost probability, and that's going to give you the shaded region between the two of them. So we're going to do 0.1587 minus 0.0062. All right, so go ahead, pause the video, see if you can try these using the table, and then when you're ready, go ahead and press play again, and then you can check your answers. All right, for this first one, we have less than, that's to the left of 2.25, so that's exactly how the chart works. So we're going to look for 2.2 right up here. And then I'm going to look for 0.05, 0.9878. This one says greater than, this is the right side, and so I'm going to have to do 1 minus the probability that z is less than -1.37. So I'm going to look over here, -1.3, and the 0.07 there, -1.37 would be 0.0853. .9147. We've got to the right again. So I'm going to say 1 minus the probability for -0.81. So there's -0.8. There's the 1, 0.2090. .7910, and then we're going to do the rightmost minus the leftmost. So probability of 1 is 0.8413. And then negative 2, 0.0228. .8185. All right. Next, it says find the bone density test score corresponding to P sub 95, which means the 95th percentile. That is, find the bone density score that separates the bottom 95% from the top 5%. So if we're talking about the 95th percentile, that means that the area that we want would be 0.95. So this is kind of working backwards. You have the area, you have the inside of the table, and you're trying to find the z-score that would do it. I'm not going to use this side of the table because 95% is more of the table. So I've got this, and so I'm going to look for 0.95, or I'm going to look for the z-score that gets me the closest to 0.95. So there's 0.90, okay, so here it is, 0.9495, 0.9505. These are equally close. Sometimes when you're doing this, you'll find one that's a little bit closer than the other. This one is, we got 10th, 100th, 1000th, 10,000th. This is 5 10,000ths too low. This is 5 10,000ths too high. They're equal as far as how close they are. So we have two z-scores that are kind of equally good, and we'll kind of split the difference between them. So we have 1.64 is the lower end, and then 1.65 is the higher end. So I'm just going to write down what I found. 1.64 gives me 0.9495, and 1.65 gives me 0.9505. And so I would say the z-score is 1.645. So if you had one that was closer, then you would just go with that one. But here, kind of going right in the middle works because they're both equally close. All right. The next one says find the bone density test score that separates the bottom 2.5% and find the score that separates the top 2.5%. So 2.5% would be an area of 0.025. And so I'm going to look for the lower one first. So 0.025, we're looking at this side. I'm going to look for 0.02. Those are going down. Oh, there it is, 0.025. So we've got negative 1.9, negative 1.96. I'm just writing that down. So negative 1.96. Now this little area up here we know is 0.025, but our table doesn't measure areas from the right, it measures areas from the left. And so if I want to know where I would look on the table, I would actually look at 1 minus 0.025, which is 0.975. That's what I'm actually going to look for on the table. And this has symmetry, so you already know what the answer is, or you might know what the answer is, but we're going to prove it anyway. So 0.97, 0.975 is right here. we got the 1.9 right there, 0.06 right there, so it's 1.96. Right, so these z-scores right here, negative 1.96 and positive 1.96, these are significantly low and significantly high because only 2.5% of the population are below and 2.5% of the population are above these measures for bone density test scores. So for the standard normal distribution, a critical value is a z-score that's on the borderline, separating those z-scores that are significantly low or significantly high. And then we have critical value notation. The expression z sub alpha, that's the Greek letter alpha, denotes the z-score with an area of alpha, and the area is actually to the right. It's measured to the right. So this is exactly the opposite of how our table gives us the measurements, okay? So I'm gonna write this in my notes because when we do this, we're always gonna have to do a little bit of math because we're measuring the wrong direction. So this is measured the opposite of the table. And you can highlight that, you can do whatever you need. So here, the instructions for something like this might say find the critical value, and they're basically saying what's the z-score if the area underneath the curve from the right is a probability of 0.04. The area under the table is a probability of 0.04, or from the right, 4% is shaded. So if I remember the empirical rule and what the percentages are, this is like 2.35%, that's like 0.15%. So this would be like shading like something like this. These pictures are to help you, they're not to make your life more difficult. So if you don't need a little picture, then just don't draw one. It's fine. So I'm looking to see what's the z-score right here when the area is 0.04, when the probability is 0.04. But my table is not going to say 0.04. It's going to be 1 minus 0.04 because my table measures from the left. It does not measure from the right. So 1 minus 0.04 is 0.96. And so I'm going to take my table. I'm going to look for 0.96. So here you can see a good example. This is 0.9599. That's 1/10,000th off. 0.9608, that's 8/10,000ths off. And so the closest one is this one, the 0.9599. And so this is the z-score that I'll use. So I've got 1.75. 1.75 is my z-score for that one. So z is 1.75. So I can write the critical value for a probability of 0.04 is 1.75. Okay, for this one, they want the critical value when the probability is 0.15 from the right. So we know 0.15%, 2.35%, 13.5%. So this is going to be like, I don't know, most of that. I don't feel like doing all that math in my head. But it seems like that's probably the majority. Okay, and we're trying to find the z-score right here. So I'm going to look for 1 minus 0.15 on the table, which is 0.85. Okay, so I'm going to take my table. Going to look for 0.85, 84, 8508. So this is 8/10,000ths off. 8485, that's 15/1000ths off. And so this one would be closer. So I've got 1.04. 1.04. All right, for this one, 88%, so we'd have all 50% of this. This is 34%, so that's 84%. And then like a little bit more, I don't know, something like that. But for our table, we don't measure it from the right, we measure it from the left. 1 minus 0.88 is 0.12, and so that's what I'm looking for on the table. I'm looking for this z right here. And these ones are equal on either side, so 1,000th above, 1,000th below. So I've got negative 1.17 and negative 1.18. So I'm going to split the difference and do negative 1.175. Okay, and then this last one, 0.97, so we've got like all but the last 3%, so that's like almost this whole thing. They're saying they want all of this. So 1 minus 0.97 is 0.03. 0.03. Oh, that's very close. 0.0301 is really close. So negative 1.88. And again, for these, you don't have to draw the picture, but sometimes it can help you make sure that your answers are reasonable.